Okay, let's look at another example. Here we have this cylinder, which is made up of aluminum, right here. And we're given the dimensions of the cylinder. And basically, the radius of the cylinder of aluminum is 0.25 meters. And the height of this cylinder of aluminum is 1.0 meters. So it's a rather large cylinder of aluminum. And it's suspended on this string. Right there. Which is being held from the ceiling. And the question is, if this cylinder of aluminum being suspended from a string, if it's half submerged in the water, half submerged, what's the tension in the string? So the question is, what is the tension in the string? All right, let's go to a new page here. So let's say that this here is the cylinder. And let's draw the forces acting on the cylinder. So we have the Fg, the true weight of the whole cylinder. And then we have the tension of the string, but the tension in the string isn't holding up all of the weight. Because the buoyant force, the water, is holding up some of the weight of this aluminum. Okay. And again, our question is, what is this tension force? Well, since this object is in a state of equilibrium, we know that the upward forces have to equal the downward forces, yes? So basically, the tension plus the buoyant force upward has to be equal to the weight of the whole aluminum object, the whole cylinder, downward. So basically, this Fg is of the whole And if we solve this for t, t equals the weight of the whole cylinder minus the buoyant force, the force that the water exerts upward. So we're going to come back to this and solve for t. But now what we have to do is work out the individual pieces. What we have to do is we have to figure out, well, what is this weight of the whole cylinder, and what is this buoyant force? Yes? So let's start off by looking at the weight of the whole piece of aluminum, the whole cylinder. That's going to be equal to the mass of the whole cylinder of aluminum times G. But we know for mass of the whole cylinder, we could substitute the density of the cylinder, which is the density of the aluminum, times the volume of the whole cylinder of aluminum. And of course, that has to be multiplied by G. So the density of the aluminum, and now for this term here, the volume of the whole cylinder. Well, to get the volume of the cylinder, what we're going to have to do is we're going to take the area of the base of the cylinder and we're going to multiply it by the height of the cylinder times G, and this is going to be equal to the density of aluminum times pi r squared, r is the radius of the cylinder, times h times G. And now I could say that the weight of the whole cylinder of aluminum equals the density of the aluminum, which was given in the problem, 2,700 kilograms per meter cubed, times pi r squared, where the r is 0.25 meters, and that whole thing gets squared, times the height, 1 meter, times G, which is 10 meters per second squared. So the weight of the whole cylinder is going to be equal to, if you multiply that out, (5,298 newtons), and at the very end we'll round for sig figs, so I'm going to leave that as that for now. So now we figured out the weight of this cylinder, and we did so by by basically, making the substitution for the density of the aluminum times the volume of the whole cylinder. Okay, so moving back, we just figured out this piece right here, the weight of the whole cylinder, and our goal is to figure out this tension here. So what do we have left to do? Figure out what this buoyant force is. So here we go. Come on, come on. Whoopsie. So the buoyant force is going to be equal to the weight of the displaced water. In other words, the weight of the water that used to be where the aluminum now is underwater. And of course, that's going to be equal to the mass of the displaced water times acceleration due to gravity. And that's going to be equal to the density of the water times the volume of the displaced water times G. But here's the big clincher. What is this volume of the displaced water equal to? Well, here we have the density of the displaced water, density of water, times the volume of the displaced water is equal to the volume of the aluminum cylinder that's underwater. Times G. So the buoyant force is going to equal the density of the water times the volume of the aluminum cylinder that's under the water times G. So the buoyant force is going to be equal to the density of the displaced water, the density of the water, times the area of the base of the cylinder times, not the whole height, but only the height that's underwater, which in the problem they told you that it's half underwater. So it's going to be half the height of the cylinder. That's the depth, or the part of the cylinder that's under the water, times G. So this buoyant force is going to be equal to the density of the displaced water times pi r squared, the area of the base of the cylinder, times half the height, because that's how much is under the water, times G. So FB equals the density of the water, which is 1,000 kilogram per meter cubed, times pi r, which is going to be 0.25 meters squared, times 1 meter, which is the whole height of the cylinder, divided by 2, because half of it is underwater, times 10 meters per second squared. So the buoyant force is going to equal, what does that come out to be? 981 newtons. So now to bring it on home. So remember, we looked at the cylinder, and basically the whole weight is going down, and we have the tension holding up some of the weight, and we have the buoyant force holding up the rest. So we know the tension plus the buoyant force is equal to the weight. Okay, and that's the weight of the whole cylinder. So the tension is going to be equal to the weight of the whole cylinder minus the buoyancy force. So we know the weight of the whole cylinder. What was that? And we know the buoyancy force. So the tension turns out to equal, and if you round to 2 sig figs, 4,300 newtons. There's the answer.